In this lecture, we are finally going to conclude this section and summarize everything we learned. This section was all about classical time series analysis. We covered two staples of time series analysis, which are the Holt-Winters model and ARIMA. Holt-Winters started from a very simple concept. Instead of just taking all the values in a time series and calculating the average, we looked at the moving average. This kind of thing makes sense when the data changes over time. We started with the simple moving average and extended this concept to the exponentially weighted moving average. From there, we looked at how the exponentially weighted moving average could actually be seen not just as a way of computing an average, but as a predictive model. Seeing this as a predictive model opened a new door for us, specifically allowing us to model the trend component. This gave us Holt's linear trend model, which improves on exponential smoothing by predicting lines at any angle rather than just horizontal lines. From there, we learned about the Holt-Winters model, which adds seasonality to the whole model. The next topic we looked at was a more general model, the ARIMA method. The ARIMA method is more general because it doesn't assume anything about the structure of your data. It's not explicit about trend and seasonality like Holt-Winters. We learned that ARIMA comes in three parts: the autoregressive part of order P, the integrated part of order D, and the moving average part of order Q. The autoregressive part is based on past values of the time series, whereas the moving average part is based on past errors of the model. The integrated part specifies how many times you used differencing in order to make your time series stationary. We looked at how to test stationarity using the augmented Dickey-Fuller test. Initially, we tried to guess ARIMA orders, sort of as a first crack at finding a good set of values for P, D, and Q. To improve on guessing, we learned that there is a more scientific approach using the ACF and the PACF. However, with modern advances in computing, it's often accepted that auto-ARIMA is an even better method of choosing P, D, and Q. This allows us to efficiently search through seasonal orders as well. For stock prices, seasonality is less relevant since stock prices typically don't have seasonality. Of course, this isn't set in stone, and others have said that some seasonal patterns do exist in stock prices. You are certainly encouraged to test that out for yourself if you think it could be true. In the end, we discovered that 30-day forecasts, which are somewhat long-term, are better predicted by the naive forecast rather than with ARIMA. This is equivalent to the random walk model, and it shows that even if the random walk model might not be exactly correct, it's still pretty hard to beat it. Now, don't be fooled. A lot of beginners might see this and think, well, what a waste of time. You could have just said stocks follow a random walk. And of course, beginners being beginners would be missing the point. Although the conclusion is simple, the methods and the reasoning are not. You now have a much better model of how stock prices behave from a statistical perspective. One useful trick for understanding ARIMA is to think about how you would implement such a model yourself. This opens a lot of doors when you really think about it, because instead of just a plain linear model, you can use any machine learning approach. This includes powerful algorithms like random forest and neural networks and other state-of-the-art techniques.